Hello everyone. In this video, we're going to be solving a quintic equation. Can you imagine? We're going to be solving a quintic. How do you solve a quintic? Is there a quintic formula? No, it does not exist. Too bad. Abel proved it. It's impossible. I know some people are going to say, oh, it's not, can be expressed in terms of radicals, so on and so forth. Guys, accept it. There's no quintic formula. So we're going to go ahead and solve it. But when I say solve it, maybe we're not going to completely solve it. We'll kind of solve it. And I'll show you some alternatives that you can use to proceed, because quintic equations are complicated. But you can start by guess and check, right? Obviously, okay, let's take a look at this equation. The sum of the coefficients on the left-hand side is 3, and I have 3 on the right-hand side, which means x equals 1 works. Yay, awesome. The million-dollar question is, what about the other solutions? How do you find them, right? Okay, let's take a look. So we just found out, discovered, whatever you call it, x equals 1 is a solution. So can I not use it to find the other factors? Sure. X equals 1 means x minus 1 is a factor. So you can basically divide this polynomial by x minus 1. And this is the second video for today, remember? If you haven't seen the other video, go ahead and check it out. That's a cubic equation. So we're doing a cubic and a quintic on the same day. How exciting is that? Now, so once you know that x minus 1 is a factor, like I said, in the other video that I made today, I used that method. I just used long division. And it takes a long time, even with the quintic, right? I mean, with the quintic, it's going to take even more. So let's do something smarter. And this is how it goes. I'm going to put the 3 on the right-hand side. Or should I say this? I'll write the 3 as 1 plus 1 plus 1. Do you know why? Each of these ones will be paired up with these terms like this. Look at that. Take a look. Isn't that beautiful? X to the 5th minus 1, x to the 3rd minus 1, and x minus 1. Guess what? Now we can factor by grouping. Like this, and like that. X to the 5th minus 1 is x minus 1 times x to the 4th plus x to the 3rd plus x squared plus x plus 1. Such a long factor, isn't it? X cubed minus 1 is difference of two cubes. We can write it as x minus 1 times x squared plus x plus 1. And finally, 1 times x minus 1. That's it. Now, x minus 1 is a common factor, so why don't we factor that out? And we're going to get x to the 4th plus x cubed plus x squared plus x plus 1 plus x squared plus x plus 1 plus 1. Uh-oh, there's a lot of ones. So that one of the factors will be x minus 1. The other factor will be x to the 4th plus x cubed. Let's add x squared plus x squared, which is 2x squared. X plus x is 2x. And 1 plus 1 plus 1 is 3. Nice, right? Well, not really. Well, we get a quartic equation from here, and there is a quartic formula. You want to know what that looks like? Look it up. You're going to see a picture on Wikipedia. I think it's gigantic. It's ginormous. It's amazing, like crazy, okay? Colossal, whatever you call it. And imagine if there was a quintic formula. We know it doesn't exist, but if there were, it would probably take several pages. Maybe you would need a book to write it. Who knows? So, how do we solve the quartic? Yes, there's a way to solve it. And we can try something like this. Let me show you. Okay? We can go ahead and do this. There's a couple different ways to go about it. First of all, you can try to depress the quartic, which means get rid of x cubed by way of substitution, and then set up factors, so on and so forth. But there's also another way to do it. I don't know if I'm going to be able to pull it off, but I'll give it a try. So we can basically try to make both sides a perfect square. So I can try to maybe leave x cubed here and put everything else on the right-hand side. Is that how it works? Probably something like this. So I'm going to try to add something to both sides to make it a perfect square. And that term is probably going to look like this. This is x squared plus x plus 1/4 multiplied by x squared, because this is x plus 1/2 squared. Did you realize what I'm doing here? Take the coefficient of x, half of that squared is going to give you the constant term, and that's what we're going to get. So we need to add 1/4 x squared. Great, let's do that. We're going to add 1/4 of x squared, and then of course you're going to add 1/4 as well. That's going to be like negative 7/4 x squared minus 2x minus 3. So the left hand side became a perfect square, but it is now x squared times x plus 1/2 squared, which I can write as x times x plus 1/2 quantity squared, like this. Nice. And the right hand side, that is not a perfect square, but that's perfectly fine. You know why? Because we're going to add more terms to make the left hand side another perfect square while making the right hand side a perfect square, and that's just going to be perfect. But it's going to be super messy, I have to warn you. Okay, are you ready? All right, let's go. So we're going to add the following. We're going to add the following to both sides. So this expression is, first of all, something squared plus 2k times that thing. Okay, 2k times that plus k squared. All right, so we got something like this. If I call this a squared plus 2ka plus k squared. And that is actually a perfect square. And it's just perfect, right? Awesome. So what am I supposed to do? Add that to both sides, of course. And what am I adding? I'm adding this. When you add that to the right-hand side, the left-hand side, we know that is going to be a perfect square. How? It's going to be x times x plus 1/2 plus k quantity squared. From here, take a look at that. Take a good look. And the right-hand side is going to be super messy, like I said, 2k x squared and then minus 7/4 x squared. That's the x squared. And then we're going to have a kx, and then there's a 2x, so it's going to be like k minus 2x. And then we have k squared minus 3 as the constant term. Okay, great. Now the right-hand side also needs to be a perfect square, which means delta, or the discriminant, needs to be 0. But there are easier ways to do it, obviously. You want this to be a perfect square, right? Obviously. And hopefully it's 1. I don't know if it's going to work, but I can try. At the same time, you also want to get something nice from here, and that probably needs to be a perfect square as well, right? Sort of. Like, think about it. This is a perfect square, right? But this isn't. Why? Because 8 isn't a perfect square. You see? So you need perfect squares. Okay, can we pull it off? Maybe. Can this be 1? If 2k minus 7/4 is equal to 1, that would be super simple, right? 2k would be 11/4 and k would be 11/8. I don't think so, but I can give it a try. So if you subtract 2 from it, 11/8 minus 2 is going to be negative 5/8. Maybe. What about k squared minus 3? K squared minus 3 is going to be 121 over 64 minus 3, and that will be negative. Again, that won't be good. So 1 didn't work. Maybe 4 will work. Who knows? But again, that's a little painful, isn't it? So I'll show you another method. Okay? I mean, not necessarily another method, but one thing that is super important. First of all, remember we're looking for solutions of this equation, right? So let's go ahead and call this f of x. Why not? We're going to do a little bit of calculus. Don't be scared. It's easy. So we're going to go ahead and differentiate this function, y. I'll show you in a little bit why. 5x to the 4th plus 3x squared plus 1. The derivative of a constant is 0 because it's rate of change. So constants do not change. Make sense? So what does this derivative tell you? It should tell you a story. First of all, notice that the derivative is always positive, which means f of x is increasing all the time. What's that supposed to mean? It means it can only intersect the x-axis at one point. So there's only one real solution, and that is x equals 1. So there are no other real solutions, and since this channel is mainly about real numbers, because I have another channel called aplusbi, which is all about complex numbers. So if you like complex numbers, go ahead and check it out. If you don't like complex numbers, go ahead and check it out because you might end up liking it, and complex numbers are fun.
So let's go ahead and take a look at the graph, shall we? And we'll finish up with that. Ta-da! There's only one intersection point, and that's at x equals 1, the solution to this special quintic. But there's no quintic formula, I repeat. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.